classes were like that pre-COVID here too, but now most classrooms have maybe 8 children, maybe.
Wow. Ah, so they do part-time class? Or?
Yeah, half are learning for New York City, half are learning from home every day. About a quarter are learning like a hybrid, so in school half time. And the other quarter, they've lost them. They don't know.
Ouch.
They, they lost the kids. They don't know where they went.
That's difficult.
Sorry to interrupt you guys. We should probably get going. Is that okay? Yeah. So good morning, everyone. This morning's speaker is Cecile Agosta. Cecile has a PhD in glaciology from Grenoble University. She then spent some time in Liège in Belgium before moving to the Laboratory for Climate and Environmental Sciences, which is quite close to Paris. Cecile is a research associate in glaciology, where her work is particularly interested in the climate and recent changes to the climate in Antarctica, but also a little bit in Greenland. Without further ado, Cecile, if you could take over, that would be great.
Yeah, good. Thank you for this introduction. So thanks for inviting me. It's a pleasure to speak to this seminar. And as said before, I'm interested in the Antarctic climate. And my first motivation for it was to quantify the Antarctic surface mass balance. So its contribution, so its atmospheric meaning contribution to sea level. But then I got really passionate to the Antarctic climate for itself. But as it is now a seminar about sea level, I will focus here on the surface mass balance of the Antarctic ice sheet. So first, I will introduce why it's important and how it contributes to the sea level. But most of you must know this part, but I don't want to lose anyone here. So yeah, this will be short on this. And then I will detail some local processes that can impact greatly the surface mass balance in the first part. In the second part, I will talk about the large-scale drivers of the surface mass balance, focusing on accumulation and snowmelt, part, also component of the surface mass balance. And then I will talk about Antarctic surface mass balance projections. So to begin, so I run a regional atmospheric model, which is called MAR, and this regional model was specifically developed for modeling the polar climates, in particular the Antarctic climate and the Greenland climate. It's because since a long time, French people had a station in Antarctica. So can you see my mouse? Yes. Yeah, okay, that's good. Here in Dumont-d'Urville. And then they opened a station with the Italians here in the central Antarctic plateau. So that's why first it was political and then it got to science, as it's always been in Antarctica. And we were lucky enough to develop this regional model with polar specific processes in it from the beginning. And it is with this model that I computed this map of the surface mass balance of Antarctica that was published a few years ago. So what is the surface mass balance of Antarctica? In fact, it's mainly the snow accumulation over the ice sheet. So here you can see that the surface mass balance is positive over most of the ice sheet, with the larger accumulation at the ice sheet margins. And I also plotted with dots the location of surface mass balance observation that we will see later. So when we integrate the snowfalls over the ice sheet, we obtain the total contribution of the Antarctic ice sheet to sea level, but it's only when we compute it over the grounded ice sheet. So the part of the ice sheet that is grounded on on rock, and there is some part of the ice sheet that is not represented here, but that is floated on which we don't integrate the surface mass balance, on which the surface mass balance don't contribute directly to sea level. So as I said, the Antarctic surface mass balance is mostly about snowfalls and sublimation of the snowfall, but you can also have some snow melt at the surface, but almost half of the melt is refreezing into the snowpack. So you can see the numbers here. The contribution of the surface mass balance on the Antarctic surface mass balance to sea level is of about 1,900 gigaton per year. So that's huge. That's almost a 6 millimeter sea level equivalent. And when we want to compute the mass balance of the ice sheet, of course, it's the difference between the snow gain by snow accumulation and the mass loss by ice discharge to the ocean. So here in this, I will focus only on the surface mass balance. But here on the ice discharge, I wanted to highlight the grounded line that separates the grounded ice from the ice shelves that are floating into the ocean. And you can see, okay, I changed the number because I integrated into a different ice mask. But the ice discharge at the grounded line is of same magnitude than the surface mass balance. So when we want to compute the total contribution of the ice sheet to the sea level, it's really the difference of two big fluxes that gives a mass contribution to sea level. So this graph is from Rigno et al. 2019, where you can see the surface mass balance in blue, change in surface mass balance through times in blue. The change is in ice discharge in red, and then the total mass balance in purple. So finally, the contribution of the Antarctic ice sheet to sea level is of about 100 gigaton per year, but with a difference of fluxes that are 10 times larger than the contribution to sea level. That's why it's really important to know how to compute the surface mass balance and its evolution in the future, because small change in surface mass balance can have great impact on the sea level. But the surface mass balance can also have an impact on the ice discharge. And it's what happened, for example, here on the Antarctic Peninsula, where increasing snow melt, increasing temperature induced increasing snow melt at the ice shelf surface, then the disappearance of these ice shelves. And it's not directly the disappearance of the ice shelves that cause the increase in sea level, but it's the buttressing effect of the ice shelf that has an impact on the ice discharge to the ocean. So here on the left side, you have the quantification of the ice shelf buttressing effect, meaning that these ice shelves are constrained because, and they are locking the ice fluxes to the ocean. If you remove or weaken this ice shelf, you increase the ice flux to the ocean, and thus you increase the ice discharge. So that's an indirect effect of increasing snow melt and runoff over ice shelves to the sea level. So yeah, I have a slide on it, but I already talked about it, so I will move to the next one. That is the first part of the talk about mainly focus on snow accumulation processes and what can impact locally snow accumulation. So first, you must know that there are very few observations of the Antarctic surface mass balance. Snow gauge, I don't know how you say it in English, but and precipitation measurement, direct precipitation measurement are not feasible because of snow being blown by the wind. And at the margin and inside you have very few snow accumulations, so it's very hard to directly measure it. So what is done is mostly indirect measurement. So with stakes, you measure the snow height from 1 year to another, and then you measure also the snow density, and you can deduce the snow accumulation. You have ice cores at several points. So they are here in the gray points on these maps, on this map. And then last measurement technique developed this last tens of years is ground penetrating radars that are calibrated with ice cores measurements that can allow to cover much larger areas, such like in the West Antarctic part of here. So if we want to evaluate the model, we first have to compare them with this measurement. But from this measurement directly, it's very hard to have a global view of the surface mass balance. So either the measurement can be interpolated. That's what has been done, for example, by Medley and Thomas in 2018. So what they did is use the spatial field of reanalysis from reanalysis. So they use the precipitation minus sublimation of reanalysis. And then they use the temporal variability of ice cores to specialize the ice cores data into the whole ice sheet. So with this technique, they obtain a grounded ice sheet surface mass balance of almost 2,000 gigatons per year. Another way to have an estimate of the surface mass balance is to use atmospheric models. So, and the most used products from our atmospheric model are from the regional atmospheric models. So there are mainly two regional climate models that are really dedicated to polar studies with a detailed snowpack in them. So that's the MAR model that I use. And there is also the RACMO model developed at Utrecht in the Netherlands. So these models, they have a detailed snowpack. For example, MAR has a 20 layer of snow and 30 meter of firms models into the model. But it also has special parameterization for the turbulent fluxes over snow surfaces and a special care to the cloud and precipitation microphysics. So here the simulation I show are at 35 kilometer resolution. So that's not a very high resolution, but it's sufficient for most parts of Antarctica. And also the first vertical layer is very close to the surface. It's at 2 meters above the surface. And last thing is the model is nudged. So the boundary are over the Southern Ocean, as shown here. And it's nudged at the top of the troposphere so that the large-scale circulation is close to the forcing field. So the regional model cannot change the large-scale circulation. It can only change what happens in the atmospheric column in the lower troposphere from above 3,000 meters above the ground, more or less. Go to the next slide. So with this regional model, I computed the surface mass balance, which I've shown already. With this model, we obtain numbers similar to Medley and Thomas. And in fact, we obtain very similar numbers than the RACMO model. Then afterward, I will, on the right, you have the surface mass balance computed with the observation of surface mass balance on top of them. So globally, we have a good agreement between the model and the observation, and between the model, the two regional models specialized for polar studies. But we'll see that if we look at it closer, we'll see large differences.
Can I interrupt?
Yeah, yeah, of course.
From Olga.
Yeah.
And she says, how are the errors estimated in MAR?
Sorry, how
are errors estimated in MAR, the MAR model?
Errors here, given here?
I'm not sure. Is that correct, Olga?
Yes. Yeah.
Okay. Here it's not the error; it's the standard deviation of interannual values. Yeah. Mm. It's one standard deviation of interannual variability. Here. And here it's an error
Okay,
estimate.
so that means they're slightly different. What Medley and Thomas in
Yes,
those,
yes, that's different.
Okay, and here this time. Okay, thank you.
Yeah. If we evaluate the surface mass balance globally by doing scatter plots, it's really difficult to decipher if a model is good or not compared to observation, because the observations are really scattered over the continent, and you have a big gradient from the coast to inland, and most model knows how to do this gradient because it's colder inside, it's wetter outside, so all atmospheric models are, even the baddest one, the bad one, the worst one, they can do the gradient from the coast to inland. It's just a matter of Clausius-Clapeyron relationship between temperature and humidity. So what's important is the ratio of the lapse rates of okay. The important thing is to know if we are able to really represent the magnitude of the surface mass balance at the coast and inland. And that's why I wanted to look at it more carefully on transects of the few transects we have over Antarctica that are mainly stakes transects. So I show here 4 transects that are composed of almost 1 stake every kilometer. And this way we can average out the small scale surface mass balance variability into a model grid box. So that's the most valuable observation we have with also a radar transects, because you have a really huge small scale variability, and particularly at the ice sheet margins. If you compare 1 stake with 1 grid box, it's totally wrong. But when you average the stakes from 10 to 20 stakes over a grid box, then you obtain a really robust value of the surface mass balance. So here you can see for each panel, on top you have the time range over which observations and the model have been compared. Then you have the number of observations by grid cell. And below you have the elevation over the grid cells. And below you have the comparison for surface mass balance. So in black you have observation. In blue and green you have MAR simulation forced by 3 reanalysis. And in red you have RACMO2 regional climate model forced by error interim. So what you can see is generally over these transects, MAR and RACMO2 are really in the middle of the observation usually, except if you go really near to the coast, you can see that the general trend is really well represented with the values well represented. But you can also see oscillations of the observation around the mean trend modeled by MAR and RACMO2. And in this paper of 2019, I've shown that these oscillations are due to drifting snow processes that are not represented in this simulation of MAR and that are underrepresented in the RACMO2 simulation. But I will not develop this now because it would be a little too long. But the details are in the paper. And here I prefer to focus on another process that is really important in Antarctica, that is the sublimation of the precipitation into the surface layer. So first I want to say that the boundary layer in Antarctica, it is really important to correct it, to model it correctly in order to have the correct surface climate at the surface of the ice sheet. For example, even ERA interim, which is a reanalysis, so it assimilates observation, it can have a bias of almost 5 degrees inside the continent. And this bias is corrected with the regional climate model because it better represents the snowpack, the turbulence fluxes, and also the clouds. And these processes are also important to model correctly the surface winds as a sheet surface. So from one side, you have low pressure here over the ocean, and a high pressure due to the polar cell here inside the continent. So at the surface, you have a surface flux going from the ice sheet, inland ice sheet, toward the ocean. On top of this surface flux, you have a katabatic wind flux that is superimposed to the surface flux. So you have a pressure gradient flux and a katabatic flux. The katabatic flux is the flux that is due to the cooling of low-level air in contact with the snow. So in order to have the correct wind at the ice sheet surface, you have to model both the large-scale circulation and these local processes. And this surface layer with dry winds coming from inland towards the ocean is really important for the surface mass balance because this wind, by going down, they experience a strong warming because of adiabatic warming compression. Because you have a very dry layer of air that is very warm, you have a strong, a very low relative humidity. And in this layer, you can have strong sublimation of the precipitation. So it was shown by Grazioli et al. In 2017 with observation made by LIDAR. And in this paper, they specialize the sublimation of precipitation they observe using a model from the European Center. And they obtain a map of the atmospheric sublimation of precipitation. So with this method, they quantified the atmospheric sublimation to be of 300 gigaton per year. So that's huge. That's almost 1 millimeter sea level equivalent. And previously I've shown that MAR and RACMO2, they give the same amount of surface mass balance when integrated over the grounded ice sheet. But here you have the map of difference between the two models. And you can see very large differences, particularly at the ice sheet margins here, where MAR is much drier than RACMO2. And by looking at this map, I wanted really to understand which model was correct and which model was wrong. And doing by comparing both model to observation, I couldn't obtain any information because most of this part where there are the main differences, there is almost no observations. And it's because I think it's a very part with a very harsh climate there. So it's hard to do observation here at the margins. But in fact, this map of difference, it looked like a lot the map obtained by Grazioli showing the atmospheric sublimation. So I had the feeling that these differences could come from atmospheric sublimation. And in fact, it was really the answer of this problem. Yeah, because in fact, we discovered that in RACMO2, atmospheric sublimation was very low compared than in MAR. And yeah, and finally, MAR was closer to the observed values than RACMO. So here we see that we can easily lose 200 gigaton of surface mass balance just by missing one process. And it's because RACMO advected too fast the precipitation through the atmospheric layer.
Can I ask a question? Do you know whether the sublimated precipitation ends up in the end? Is it
it's exported. Yeah, most of it is exported through in the form of water vapor outside of the ice sheets. Okay. But then it's you see that it's compensated by places where MAR has much larger accumulation than RACMO. This is because precipitation is advected further inland in MAR than in RACMO2. And this I don't know yet if it's because we have more finally more water vapor in the atmosphere that is then re-advected inland or not. That's the question still open. I have the feeling that it's different processes that are involved, but I'm not totally sure of this. Finally, I wanted to highlight that when we force MAR by different reanalysis, here I force MAR with 6 reanalyses that are listed here. Among them, ERA, GRA, NCEP 1 and 2, MERA 2 and 20CR. And on the left, you have the precipitation minus sublimation from the reanalysis. And on the right, you have the surface mass balance from MAR. And from it, I subtracted for everything, I subtracted for every field MAR forced by ERA and TERI. So what we can see here is when we look at the snow accumulation from reanalysis, it's very different from what is obtained with MAR. And some of them are very wrong, like for NCEP 1. And it's corrected when we use MAR. So even NCEP 1, downscale with MAR, we obtain a correct surface mass balance pattern. So, but when we look at the temporal variability of the surface mass balance, then it's really correlated with what is in the forcing reanalysis. So yes, the regional model can correct global climate models and reanalysis, but it cannot correct the large scale calculation and thus the temporal variability of the surface mass balance. So that was my second motivation. Yeah, I am already, so I will go a little faster. Was to do projection of the surface mass balance of the Antarctic ice sheet with downscale with the regional model to correct the global climate model for the missing processes specific to this polar region. And for this, I wanted to select global climate models that are not too bad over the Southern Ocean. Because my computing resources are limited, I don't want to downscale the worst model for Antarctica. And one motivation was to give from global climate model forcing to the ice sheet model and resolving the polar processing with the regional climate model. That was the initial goal of this project. So CMIP, you know this, and ISMIP is the ice sheet model intercomparison project. So as I say, I wanted to select my large-scale forcing, and it's because I know that when you have biases in the large-scale forcing, you will have strong biases in the surface mass balance at present. And so it's difficult to be sure that you never know if your projection will be good, but yeah, you can maybe improve your reliability by choosing your forcing. That was an example of the impact of the large-scale pattern into the surface climate for Antarctica that was published by Marshall and Thompson in 2016 here. So on the left, you have the difference of large-scale fields from SAM plus minus SAM negative pattern of this positive pattern of the SAM minus negative SAM of the SAM. What it means that in fact, the positive SAM is when you have a large pressure gradient between the pole and the middle latitude in the Southern Ocean. And the negative phase is the reverse. So here you can see that when you subtract the negative phases to the positive phase, you increase your wind around the Antarctic ice sheet. And so the westerlies are closer and stronger and closer to the ice sheet. And then you have a really high cold anomaly inside the Antarctic ice sheet. And in fact, in global climate models, you can easily have a large bias in pressure gradient in the Southern Ocean that will have a large that will induce a large bias in, for example, surface temperature and surface mass balance. And we also have shown that if you have a large bias in sea surface condition, you can induce strong bias in surface mass balance in the regional climate model, because sea surface conditions are an input of the regional climate model. It's forced from the forcing global climate model. So in this view, I evaluated several fields from global climate model, first for CMIP5 and for atmospheric fields. And then to select forcing for the ISMIP6 project, we still had CMIP5 only, and but we evaluated both atmosphere and ocean, and only for Antarctica. And then I'm currently working on evaluating both CMIP5 and CMIP6 global climate model for atmosphere only, but both for Antarctic and Arctic. And this is because there is a European project that is beginning that is named PROTECT, that aims at continuing the ISMIP, so the ice sheet model intercomparison project in the next years. And they need atmosphere and ocean forcing too, for both Greenland and Antarctica.
Sorry, there's a question in the chat again. This is from Allegra.
Yeah.
She's saying sea surface conditions aren't from observations, question mark.
No, sea surface condition, yeah. When you force by reanalysis, sea surface conditions are from observation. They are from satellite observation. But when we force by global climate models, sea surface conditions are taken from the global climate models. Okay. So what I evaluate in the global climate model is the humidity fields first. So I use integrated water vapor, and I subtract. So I do the time mean over the late 20th century, beginning of 21st century, and I subtract the reanalysis. So here on the top right, I subtracted here the ERA 5 reanalysis to each global climate model from CMIP 5 and CMIP 6. And at the bottom, you can see the 5 other reanalysis. So we can see that in the NCEP reanalysis, there is a difference in humidity compared to ERA 5, for example. And I take the domain of above 50 degrees north for the Arctic and below 40 degrees south for the Antarctic. So I do the same for, yeah. And then my metric is the RMSE so the spatial RMSE over these domains. So I do it for several fields, including air temperature at 850 hectopascal, and for sea level pressure as an example. So I put it the sea level pressure. And what we see that there is, by just looking at it, an improvement in the representation of sea level pressure patterns in CMIP 6 compared to CMIP 5 for the Arctic and also for the Antarctic. So I did it for several metrics, 2 representing the large-scale circulation as surface level pressure and the 500 geopotential height, metric representing the air temperature at different pressure, and the IWV that is representing the humidity, and then the 2 sea surface condition metric. So the sea surface temperature in summer and the sea ice concentration in winter. And so the metric is the RMSE divided by the median RMSE total for CMIP 5 and CMIP 6. And for example, this way, you can see that for CMIP 6, the sea level pressure is better represented than in CMIP 5 for the north and the south. Next, I combine these metrics. And I wanted to take one, so each time I combined 5 metrics, one for the sea level pressure, large-scale circulation, 1 for temperature, 1 for humidity, and 2 for sea surface condition. And I wanted to test a different combination to be sure of my ranking of the model. So that's the scores you can see here represent four different combinations of the metrics. And you can see that, and I rank it by the mean of the metrics. So what you can see is when a model is good for a metric, is on the best half for one score, it's most likely in the best half also for the other 3 scores. So this way I can decide to choose my models into the best half of the score that so the first 2 quantiles here. And from them, I can use different criteria to select the model. So I decide that the best, this model of the best half are suitable for my, my modeling. So in fact, this way I rule out some models, and then I have a list of not ruled out yet models that I can use to force my regional climate model. And you can see that, for example, the GIS model, it's very good for the south area, so the southern, the Antarctic region, but it has a bad metric for the northern area. So here I decide to choose models that are good both for the north and the south. So from, I just evaluated the model here for the global mean. So for mean field, but we had the focus this last year on extreme events particularly on atmospheric rivers events that are advection of humidity around narrow corridors, and it brings heat and moisture over the Antarctic ice sheet. And I will go rapidly to it because I want just to show the projection later. So I will not present the atmospheric river part, but we published recently a paper in Nature Geoscience that shows that these atmospheric rivers are a rare event, but they contribute to a large part of the melting over the Antarctic, the West Antarctic ice sheet. So in fact, so I come back here, you can see that it's present for at most 5 days per year over on the Antarctic ice sheet, but it's responsible from 10 to 100% of the melting over the ice sheet, depending on the season and the location. So it's because these events, so they bring, so they are detected because they bring a lot of moisture, but they also bring a lot of heat also, and both combined creates special condition that increase the melt. And of course, you can imagine that these events also have an impact on the snowfalls. And so it doesn't represent a large part of the snowfall, the total snowfall, but it's responsible for most of the internal variability of the snowfall. So in future work, we will relate this more closely these events to large-scale circulation. So finally, I go to projection. So with the regional climate map, we downscale 4 global atmospheric models, 2 from CMIP 5 and 2 from CMIP 6. So the 2 CMIP 5 model here are the light blue line, and they are around the CMIP 5 mean increase in temperature by the end of the century. But the 2 CMIP 6 model, they are at the upper range of the temperature warming in Antarctica at the end of the century, as you can see in this graph. So they are the 2 orange lines here. And their temperature increase is much larger than in CMIP 6 mean and in CMIP 5 mean. So CMIP 6 is in red and CMIP 5 mean is in blue. So from this, we obtain maps of changes in surface mass balance by the end of the century, obtained with MAR, so the regional climate model applied to these 4 GCMs. And what we can see generally is an increase of the accumulation inland and a decrease in surface mass balance at the ice sheet's margins, so mostly at the ice shelf surface, because there is there a large increase in snow melt and meltwater runoff. So we separated so the changes over the grounded ice sheet and the ice shelf. So grounded ice sheet is on the left and ice shelf is on the right. So here you have the increase in snowfall for the 4 simulation over the grounded ice. So there is a large increase over the grounded ice and a really small increase over ice shelves in snowfall. But if you look the meltwater runoff, you have an increase over the grounded ice, but you have a much larger increase over ice shelves. and it's in gigaton per year. So the grounded ice is much larger than the ice shelf. So you can imagine the amount of snow melts and meltwater runoff you obtain over ice shelves. That's huge. And we found that this change in snowfall and runoff is modeled by MAR, is really related to the change in air temperature in the forcing GCM. So here we relate directly the snowfall anomaly and runoff anomaly to the temperature anomaly in the GCM. And the aim is to apply the relationship to the whole set of CMIP 5 and CMIP 6 GCMs. And we have different behavior over the grounded ice and the ice shelves. So applying this, and we combine snowfall and meltwater runoff into the surface mass balance, we obtain this relationship with near surface temperature. That is generally an increase in surface mass balance over the grounded ice and a decrease in surface mass balance over ice shelves. So we apply this relationship to CMIP 5 and CMIP 6. And what we obtain is a large spread of change in surface mass balance at the end of the century, with generally larger increase in surface mass balance for CMIP 6 than for CMIP 5 over the grounded ice. And reversely, over ice shelves, we have a much larger decrease in surface mass balance over ice shelves in CMIP 6 than in CMIP 5, but with a very large spread in CMIP 6. So you go from no change in surface mass balance over ice shelves to a large large decrease in surface mass balance. And it's of course dependent of the scenario of the surface. So this is the response to different SSP in CMIP 6. Yeah. And when we look at the spatial change in MAR compared to the forcing GCM, we can see, so what we see here on the left is the change in surface mass balance modeled by MAR, and on the right, it's computed directly from the GCM. And in fact, you have the same spatial pattern, more or less, but the largest difference between the two are over ice shelves, when you can have much larger snow melt and meltwater runoff in the regional climate model than in the global climate model. So I conclude now. Sorry for being so long. I think it's okay. Yeah, so to conclude, you have very specific processes in the Antarctic ice sheet, and particularly on the boundary layer of the Antarctic, that result from the interaction of the snow with the atmosphere. And this induces a large impact on the surface mass balance. So if you want to model correctly your surface mass balance, you need to model correctly your snowpack and the turbulent fluxes, and also the clouds and precipitation interaction with the boundary layer. And but we are still wanting to improve the regional model and also global climate model for these processes, and that's why there is a huge project beginning this year that aims at measuring these fluxes at several locations in Antarctica, and combining this with isotopic water isotopes measurements in the water vapor and in the snow in Antarctica. There is still a badly quantified contribution of the drifting plus sublimation to the surface mass balance, and we are finalizing a paper on it that I hope will come out soon. with a new blowing snow scheme included in the MAR model. We will develop in the next year also the role of extreme events on the surface mass balance in Antarctica to know if, for example, atmospheric rivers are well represented in global climate models and how they link to large-scale circulation patterns. And there is also a project beginning on it this year. And finally, we are doing more simulation with MAR, so regional downscaling more global climate models with the RCM. And we are willing to improve our statistical downscaling from this dynamical downscaling simulation. So thank you for your attention, and I'm happy to take any question.
Thank you. I should have some canned clapping. I always say that at the end of the talk. Thank you very much. Fascinating talk. So there are a couple of questions in the chat, and I hope people don't pick on.
Maybe I can. Okay. Yeah.
So I think the first one's come from Allegra.
Yeah.
Do you have any questions at this point?
Did the air melting change over that 40-year period? Huh. I have this for the snowfall, but not for the melting. I don't have the answer now. I'm sorry. Yeah. I think I can find the maps later on. I think yeah, there are some change, but it depends of the sectors. But I can't remember exactly. Yeah. How do you compute runoff? Okay. So in MAR, you have a detailed snowpack model in which the snow melt, so the meltwater is allowed to percolate and it can refreeze in the snowpack. So finally, what we call runoff, it's the meltwater after refreezing. But it's not really, yeah, there is no driving routing to the ocean, in fact. So in each grid cell, every meltwater that is not refreezed is called runoff. If surface melting, is it okay? Let me know if you want more details on it. Okay.
And then there's a question.
If surface
melting, thank you.
Yeah, okay. If surface melting increases over ice shelves, could you discuss implication for their future stability? Yeah, an effect on the entire. So that's the whole point of the following work. So what we want to do is first to have special. So we have only 4 simulations of increase of runoff over ice shelves with MAR, and it will be good to have more simulation and also to apply the kind of statistical relationship we found for the total meltwater. We could do it spatially, so we are working on it to have maps of surface melting for every CMIP GCMs, and then yeah, that could be used to force ice sheet models. And then the second thing we would like to do is to improve our routing, meltwater route. I don't know how to say. So the meltwater currently, as I said before, it's just disappears from the ice sheet magically in MAR. And what we want to do is being able to have meltwater rivers over the ice sheet, and also to better model how the snow hydrology in the MAR model. And this could help deciding if meltwater has really an impact on the ice shelf stability or not. Okay.
I think maybe you might have said, but do you have a representation of ocean melting of ice shelves?
Ocean melting, you mean by below? Or?
Yeah, in like ocean cavities.
Sorry. This is another part of modeling. This is a coupling of the MAR model with a regional ocean model.
Is that represented in your simulations?
No, currently it's not represented. Okay. Yeah.
Do we have any questions from anyone?
Since no one else is asking, I'll ask. So how are you going to use the water isotopes to constrain the surface mass balance?
Yeah, first we want to use water isotopes. So we will measure water isotopes in the water vapor with Picaro analyzers. And first, our aim is to better constrain the model parameterization for water isotopes. And then we want to combine ice cores data, so accumulation and water isotopes, and modeling. So I am implementing the water isotopes in the regional climate model currently. So we want to combine our understanding of water isotopes in the model and the ice cores data to see if we can reconstruct particular events like atmospheric rivers, or if we can reconstruct certain climate variability patterns.
And so you're mostly just looking at deuterium, or are you looking to try to also look at the DXS and back out the moisture provenance, or?
Yeah, first we want to, it's just, it's in the future. It's it's not for the, I don't know. It's a really challenging project, and it will be in the next years, so it will not be immediate results. But the aim is to combine all constraints to reconstruct climate patterns. But so first we will just use the absolute value, so the delta O18, the 18O and deuterium, and then use the deuterium excess. But it will be really not immediate results. Yeah. Are there any satellite observations that could be helpful to confirm your results? Yeah, there are some things we can still do with satellite observations. For example, there has been some results about the cloud properties using DARDAR products published recently, and I've still not used it to evaluate the model cloud properties. So it's something I want to do. And I think from satellite results, it will be the most interesting thing to do, because clouds are really crucial for the surface energy balance and for the surface mass balance, and for isotopes too.
We have a comment from Laurie.
The atmospheric rivers in satellite laser altimetry. Yes, in fact, in satellite. So that I don't know this paper, but I think it's the snowfall induced by atmospheric river, I guess. So in fact, there has been large snowfall anomalies in the drowning Montland area, for example, that were caused by atmospheric rivers. And it's really, it was really big events, very well documented. And such events are quite rare. They were quantified to be unique in the last 60 years. And it's of same magnitude as the ice discharge change in this sector, so that's huge. So a few atmospheric river events can, I'm not surprised that it can be seen by satellite altimetry.
So just to follow up on that, I think you were saying that the overall effect of atmospheric rivers is more of a mass loss through melt rather than mass gain through snowfall.
Yeah, it's because I didn't develop the snowfall part, but it's in fact a big part of atmospheric river issues. Because if you are, so if you are, I can show, where is it? No, it's not. Yes, it's after this. So here I've shown the impact on melting events, but it's really confined over the ice shelves mostly. But atmospheric rivers are detected by the humidity content in the atmospheric column, and in fact they are associated with large snowfall events too.
So at lower altitude, the melting winds, and at higher altitudes, the excess snowfall winds.
Yeah.
Okay, all right, thanks.
Yeah, sorry.
But isn't it, I mean, there's heat transport with those also, right?
Yes.
Which isn't trivial.
Yeah, but inland, you mostly have increased snowfall events, large snowfall events induced by atmospheric river. Yeah. Even if warm, it's not warm enough to induce mass loss inland. Ah, yeah, Jonathan is here. So he's a specialist of atmospheric rivers. Okay.
Sorry, yeah, I forgot that the East Coast had daylight savings, so I thought this was beginning at 5 p.m. in France.
No problem.
But yes, if you have any questions about atmospheric rivers, I could help.
Yeah, there was a question, Jonathan, about the melting trend due to atmospheric river over the last 40 years. Is there melting trends due to change in atmospheric river trend?
So the question is, are the trends in melting related to the trends in atmospheric rivers?
And is there so?
That is a good question. We haven't done the analysis yet. The only one we've done was with the explaining snowfall trends. Melting trends, we still are trying to grasp like the full picture of where what melt is being triggered by what across Antarctica.
Sorry, Jonathan, what did you say? What melt has been triggered by?
Oh, I mean, like we in the research we've done, we can establish that atmospheric rivers have triggered melt in Western Antarctica, like Marie Berland, and also on the Antarctic Peninsula. But we haven't done the full like Antarctic-wide analysis of melting that occurs over the whole continent to be able to confidently say like what trends are being directed by atmospheric rivers and what could be different other sources of melt.
Yeah.
Thanks. Yeah, I'm sorry about the mix-up with the timing. Sounds like you were unable to join us, but maybe I can pass to you to do a talk. Do we have any final questions from anyone? We're a little bit over time here, so we should probably close up soon.
Yeah, okay.
It's a very nice talk. Thank you.
Yeah, thank you very much.
Thank you. Yes.
Okay.
Okie doke. Yeah, thanks again, Cecile, and thanks everyone for joining us. I hope you have a good rest of the day. Okie doke.
Okay, thank you very much.
Bye, everyone.
Bye.